The mechanism of acidic cleavage of ethers. So if we have an alkyl ether, like this one here, we have an alkyl, or a dialkyl ether, I guess is what it really is. So we have an ethyl group over here, and we have a propyl group on the right side, because we have 1, 2 carbons here, and they have 1, 2, 3 carbons here. So if we treat that with HBr and heat it, or we could use HI as well, HCl doesn't really work very well, and HF will not work for the acidic cleavage of ethers. You probably or maybe would have memorized from class that what you'll end up doing is you'll end up breaking these two ether bonds. So you'll end up with an ethyl bromide because of the bromine, plus you'll end up with propyl bromide plus water. So, and a lot of people tend to memorize these kinds of things. They say, okay, I have a dialkyl ether, I treat that with a strong acid, I heat that, I break these two bonds. These carbons, both carbons that I've labeled 1 are attached to the halide, and then I have water left over. But what I think is a good idea is to really look closely at the mechanism of this reaction, and it might help you solve these kinds of problems in the future. So we have our strong acid, which is hydrobromic acid. So what's going to happen is that's going to protonate the oxygen of our ether. So we're going to get a protonation on our ether. So now that it's protonated, either side could be a good leaving group. Because it's protonated, we could lose this ethanol or we could lose this propanol, either way. But you can just arbitrarily say, okay, well, now that I have bromide floating around in my solution, that's going to act as a nucleophile. I'm just going to choose the ethyl side. If you chose the propyl side first, that's fine too. So what's going to happen is that we're going to attack that, and then we're going to